recording now. So we appear to be going there. Once again, this is Ralph Johnson. This is our Tuesday, our third Tuesday of the month webinar series. And this month's topic is on relative density. So I will mute myself and turn the program over to Peter.
Well, hello, everybody. We're going to talk about a topic that I find very interesting, and it's one of the cornerstones of our understanding of forest measurement. And I was excited when Ralph asked me to give a webinar on this topic because it's something that I'm personally very interested in. So we're going to be talking about measuring forest density, and we're going to look at some of the concepts and focus in particular on Curtis's relative density measure. Some of you may know that Bob Curtis, who is the Curtis of Curtis's RD, has spent most of his career with the U.S. Forest Service here in Olympia at the Pacific Northwest Research Station. I worked at the PNW station as well for 7 years before coming to work at the DNR at the beginning of 2013. So I actually know Bob Curtis fairly well. On the screen here, there's Bob in a photo from a Western Menstruationist meeting a couple years ago. And for those of you who don't know me, there I am in the same photo. I sat down with Bob last week to go over some of the things I was going to talk about to make sure I wasn't off base, and got some additional information from him. And I feel like I've been lucky to get to interact with him over the years. So I'm going to talk about kind of the basic concepts of density, what we're trying to accomplish when we measure density, what does this mean? And then we'll look at some of the specific measures of density that are used in forestry, and we'll focus particularly on Curtis's relative density. We'll kind of wrap that up with just some additional thoughts about density and some of the things I find interesting when we're measuring density and trying to relate that to other aspects of forest growth and management. So density is a key concept in silviculture and forest mensuration, and there's lots of terms that float around that you may have heard at one point or another in your school or at meetings and so forth. And there's a number of topics, number of kind of keywords that all relate, in my opinion, to this concept of density. Some of it's, density takes us sort of to the theoretical realm with the -3/2 power law. It's rare in ecology or in forestry that we get something that's so powerful that it becomes a law, to things that are quantitative that we just talked about, sort of stocking. Is something understocked or is it well stocked? So there's a number of concepts that relate to density that we may have heard about, we may sort of use loosely, and at other times very specifically. And I'm going to touch on a number of these during the rest of the webinar. So why do we really care about density, and what are we, why do we need this sort of way of measuring forests? Well, density relates to growth, both growth of individual trees and growth of stands. It relates to mortality. I think it's all pretty clear to us how density relates to growth and mortality. It can also relate to tree form and other aspects of individual trees. Tree bigger in areas where there's environmental stresses. We often think lower density stands are going to result in more vigorous individual trees. Density affects tree form. The height DBH ratio and other aspects of tree form are affected by density. Wood quality, both how long trees retain lower branches, for example, and the annual growth increment are also related to density. Density also has an effect on the environment. The development of understory is related to density, and the quality of wildlife habitat is also related to density. So there's just, it really just captures, in some respects, the full range of topics that we're interested in forestry somehow relate to density. So I'm going to kind of make a distinction between density and stocking, and some of these definitions are adapted from the Society of American Foresters dictionary and some other sources. But density is a quantitative measure of crowding based on some formula involving tree size and number within a given area. And really, in my opinion, what we're trying to do with measures of density is put everything sort of on the same scale. And you might say, how many 10-inch trees does it take to make one 15-inch tree? It's there's not an obvious way of doing that. You can think of many different ways of doing it, but we're really trying to put everything on one scale so that we can communicate that information and say, across a range of diameters and maybe even a range of stand structures, we might say we want it thin when we hit a particular number with density, or we understand that we're reaching a point where we're getting a lot of density-dependent mortality based on a single number, so we don't have to sort of qualify that by using multiple numbers. So we want just one number to describe a forest condition. And this is really what makes density interesting, because it's not obvious, going back to my analogy, how many 10-inch trees it takes to make a 15-inch tree. Really depends on how we measure density and sort of some of the assumptions that go into the formulation of our density measurement. Stocking is sort of the vernacular. It's a subjective categorization of density relative to some desirable level. And so we can say that stands stocked, that stands understocked, that stands overstocked. These aren't numbers, these are categories. And even those oftentimes have special meanings, which I'll talk about. But in a general sense, density is a number and stocking is a category. So I went back to say we want to be able to communicate certain things with a single number when we have measures of density. We want to say when we reach a certain number, we know something about the stand without having to go into a lot of detail about other aspects. So what kind of thresholds do we want to capture with our density measure? So let's kind of imagine that we're coming up with an ideal measure of density. Well, we want to know when something's understocked. We want to know when the density is below a desirable level. And oftentimes, this is a point where the trees do not fully occupy the growing space. So here's an example of what we might see, sort of looking from above an understocked stand. But we have to also jump back and have a little context here, because we have certain situations where a stand that doesn't completely capture the growing space is still well stocked. It's not understocked. So we can imagine a young stand. We can say we planted at a certain level, the trees are healthy. This is a well-stocked stand in terms of regeneration, even though it doesn't fully occupy the growing space. I want to make that distinction, kind of to point out that stocking has a range of meanings within a particular context. But by and large, past that early stage, we think of things as understocked when they don't fully occupy the growing space. We now have a fully stocked stand, and here we think the trees are effectively occupying all the growing space, but they still have ample room for development. And that's an SAF definition. So I think we get a general feel for that when you look at a stand. It's no longer a bunch of seedlings planted. It now looks like a forest. And we might say the stand's fully stocked. And then we have an overstocked stand, and this is a case where trees are occupying growing space so completely that growth is slowed, and a number of trees are oppressed or suppressed. I'm not quite sure what the distinction here is, but that's another SAF definition. We often think of an overstocked stand as at some point we have density-related mortality. Again, these are value judgments. One person's overstocked stand might be another person's well-stocked stand. It depends on what you're trying to accomplish, but in a general sense, we're looking at an overstocked stand. Growth of individual trees is slow, and we're experiencing some level of mortality. So why do we care about these different stocking levels? Well, for one reason, we care about it because of productivity. And we're going to look at a couple ways of relating stand density to productivity. And the first one is looking at the growth of individual trees. So this is the average tree growth. And the first area here is going to be our understocked stand. Basically, trees are growing just as fast as they can. There's probably not enough of them to influence each other's growth at this point. And there's a range. So going back to that new young stand, there's going to be a period of time where those trees are growing without really influencing each other, and they're growing as if they're in the open at that point. We would then enter a phase, and again, we need to keep our keep clear that we're making a distinction between individual trees in this case, and then we'll look at stands later, where growth is starting to be affected. We're turning the corner. We're getting to the point where the trees are crowding each other, they're competing for resources, and on an individual basis, growth is decreasing. And then we might enter a phase where we're just really seeing a decrease in individual tree growth. We oftentimes, this is good to be aware of, but we manage typically at a stand level, not at a level of an individual tree. And so we're looking at the same categories at a stand level at this point. And again, we'll talk about this understock period where, hey, our stand level productivity is not as great as it could be. We have growing space that's not unoccupied, we have growing space that is unoccupied. We have sort of resources going to other places other than tree growth. And so this first phase of productivity, as we get to greater density, we're increasing productivity, and then we turn the corner, and this is another interesting phase of growth here, this phase 3, and it's this idea that there's a plateau of productivity. And stand density, again, is still increasing from left to right, but we're thinking there's some level of density where productivity is basically at a plateau. We'll talk a little bit later about what that means. Another way of looking at this is what's called the Langsaeter curve, and we're capturing sort of the same concept here. With the Langsaeter curve, one of the concepts is that there is quite a range of densities of which our stand level volume increment is about constant. And what we're saying here is we move, say, from right to left, we have fewer trees, maybe we bend the stand, but our expectation under this paradigm is that we can remove trees, and the residual trees are going to grow fast enough to make up for those trees that were removed. So there's some range of stand density where we can manage and get about the same volume increment per acre for the stand. But this curve actually has a decrease in volume increment at very high densities. And again, these are some kind of uncharted waters in terms of what really happens in this range. Okay, so thinking about these ranges, we want to have sort of some markers with our stand density measures. We want to have a line that tells us when we've gone from an understocked stand to a fully stocked stand. So we'll call that the B line. And we want to have a line where we've gone from a fully stocked stand to an overstocked stand, or at least know what is that high level of density. What's the top of, that we can expect? And we can call that the A line. And so I would say any density measure has to be able to deliver basically a single number for the B level or A level, or somehow make it easy to convey the information of when you're going from understocked to fully stocked and fully stocked to overstocked. You know, as I was putting this together, I realized it's very silviculture oriented. We're not talking about how stand density affects habitat and so forth, and we'll touch on that a little later, but we're really kind of talking about density in this classic silvicultural framework. I just want to acknowledge that, yes, there's other reasons to be interested in density. So if we were to create some sort of model like this, it would also be nice if it worked for all site classes, so we didn't have to have an extra variable involved in deciding where the A line and B line are. So how are we going to establish where these lines are? Where's that place between understocked and fully stocked? Well, if we go back to the Langsaeter curve, how about the point where we go, this red circle here, where we've reached that plateau of productivity? That would be nice. That's really a very sensible place to say we're fully stocked, when we've reached a point where additional density moving from left to right doesn't yield more productivity. So we reach that point where we're dense enough to get full productivity. That'd be great, but it's not practical because we don't really know where that point's at. We don't measure volume increment over time in a stand. We have to have some way of going into a stand and just measuring it once and getting some idea if we're at that point, that B-line that I talked about. So it's not practical. What by and large people have gone to for young unthinned stands is, we'll say we've reached that full site occupancy at the point of crown closure. And different density metrics have embodied this to some degree in different ways. So once we hit crown closure, it's reasonable to think we're fully stocked. And from kind of a crown-centric perspective, that makes sense. The crown is the engine of productivity, and the bigger the crown, the more crown area covering the acre, presumably the more productivity we're going to have. So this is embodied in the concept of crown competition factor. This was another measure of density that I'm not going to talk anymore about. You may have heard of it, CCF. Sometimes we use it in forest growth model predictions. So basically, once you hit a CCF of 100, if you think of it as a percentage, we have full site occupancy. And a really important point, I think, about many ways of measuring forests is we oftentimes don't measure things directly. So even with the CCF measurement, we don't go in and start measuring crowns and looking at crown closure and so forth. We use an equation that's based on DBH and maybe the DBH squared of open growing trees. So basically it's sort of the maximum crown area per unit of DBH. And I bring this up because, and I'm not going to go into a lot of detail about this, but Curtis did some really neat work showing that many measures of density basically are going back to the same thing, and that is how much space are trees taking up? What's the minimum or maximum amount of space that trees can take up in a forest and either reach that level of full productivity or start dying once you reach that minimum amount of space each tree is allotted within the forest. So it's we look at things in different ways. We look at things in the crown competition factor approach, for example, but really virtually every measure of density that we've come up with tries to get back to that idea of how much space are trees taking up and then aggregating that. Okay, let's go back now. We've decided the B-line kind of by and large is going to be that point where we've reached full site occupancy. Now, how about that A-line? How do we know when we're reaching that point where we're overstocked? Well, again, if we're interested in productivity, stand level productivity, it would be really nice to know where are we so dense that our productivity is decreasing. And this could be net volume increment, for example. So where is it we're at a point the net volume increment is actually decreasing because we're at such great density? Maybe it's because of mortality. Maybe it's because each tree is growing slower. But hey, that sounds like a great place to put that A-line. Again, it's not practical. We don't follow trees in productivity, it's hard to know when trees have died, whether it's density-dependent mortality or other sources of mortality. So I'm pointing these out because we were trying to capture sort of an ideal, but we end up with something else. Well, there's been another way of deciding when we're at that point of maximum density, or at least close to that point of maximum density, or overstocked. And basically, it's an empirical approach. It's just like, and what I mean by that is, hey, let's go measure a bunch of stands, and let's find the most dense stands based on some sort of criteria. And that high level of density is going to capture the A-line or something close to the A-line. And I'm going to talk more about the SDI approach, which is shown here, but that's really what what's been done is looking at a bunch of stands, making the assumption that some of those stands are at the point of maximum density, and then trying to draw a line and put a value on that upper level of density. Okay, so now we have our benchmarks. This is what we want. We want to be able to identify stands that are understocked versus fully stocked, and those that are fully stocked that are overstocked or nearly overstocked. Now we have our goals in mind. Let's figure out how to measure that. How are we going to get those magic numbers to tell us where the A line and B line are? Well, let's be simple. Number of trees. Maybe we'll just use number of trees. Well, it's obvious this isn't going to work because there's big trees and there's little trees, and you can't just add up your number of trees and expect to get something meaningful out of it. So we'll just cross that off the list. We're not going to go further. Except there's certain cases where number of trees is adequate for a stocking level. And there's regeneration surveys, again, where we might say, hey, if there's 2 trees per plot, for example, that are above the minimum size, that plot is stocked. So we know just based on number of trees in this sort of narrow situation that we can decide what's understocked and what's well stocked. And you know, I just want to bring this up because it's there's certain applications where very simple measures of density are adequate. How about basal area? We all know what basal area is. It gets past the problem of number of trees because big trees get weighed more heavily than small trees. But how about we can just use basal area? And okay, that seems reasonable. Let's see if basal area will work for a line and B line. Can we identify these lines just based on basal area? And I'm going to show a couple of graphs that are based on the FRIS data, the original FRIS data. And so these are stand measurements on DNR land. They came from the original inventory. And I make that distinction versus what we see in FRIS later because later on we use FES to project FRIS forward to update it, and that has its own internal logic. So we want to go back to the raw data. What can the raw data tell us about about using different density metrics? And what I've done here is each of these points is one of our stands measured in FRIS. And I've just plotted basal area and QMD. And if we want to use basal area for an A line, we'd expect some top level of basal area that's constant across sizes. And if that works, we're good. Basal area is a reasonable level measure of density for the upper level. I used the crown competition factor approach using equations for Douglas fir to draw this green line and saying, hey, given a QMD and a basal area, where's that lower level of density, that level we need to be fully stocked? And what we were looking for here is, can we just draw sort of a straight line for a level of basal area to reach this upper level and lower level? And I drew this red line in, and it doesn't work very well, basically. We don't see, when stands have a low QMD, they just don't reach the same level of basal area as those that have a higher QMD. And we measured enough stands, and I think we can be confident that we would have seen that maximum stocking level if it existed. So in other words, basal area alone doesn't work. There's something else going on here. There's an interaction between QMD and basal area. So the maximum amount of basal area we ever see for, say, a 8-inch QMD is maybe 200, and for a 12-inch QMD is maybe 350. So we can't put everything on the same scale just with basal area. That's too bad, because I like basal area. It's really simple to measure. Okay, well, basal area failed. I think we need some sort of combination of basal area, QMD, and trees per acre. And it's very easy for me to come to this conclusion because I already know the answer, that this is the same conclusion everyone else has come up with as well. The first measure of density that I'm going to talk about is the Gingrich stocking diagram. This is for central hardwoods, particularly oaks. I did my PhD at Penn State University in the central hardwood region, and the Gingrich stocking diagram was our basic density management diagram. And so not coincidentally, the Gingrich stocking diagram has our A line, this point of overstocking, and this is an empirical point. So basically, this is after viewing enough stands, they had this idea that, yes, we can draw the A line. This is the point at which you're overstocked. Presumably, your volume increment is suboptimal. You're experiencing mortality and so forth. Then you have this this green area, this fully stocked. This is typically where we want to manage within. Then here's the B line. It's done just the same way as I talked about based on crown competition factor. The Gingrich stocking diagram also has a C line. So this understocked range, there's sort of understocked and there's really understocked. So the idea here is if you're between the B and C line, the expectation is within 10 years, you're going to grow from the C line to cross the B line. So you may be understocked now, but you'll reach fully stocked within 10 years. So a couple things here. One is that these lines are curved. So the x-axis is trees per acre, the y-axis is basal area. So if we know trees per acre and basal area, we can find our spot on the Gingrich stocking diagram. They have a different, they produce a different one for small trees here on the right and large trees on the left. So I'm pointing out these lines are curved because they have the same problem we had. There's no simple way of just putting trees per acre and basal area on a graph and sort of having a nice straight line to establish different stocking levels. The Gingrich's stocking equation is down here at the bottom, and curved lines are typically caused in equations by things like powers. So here's something to the power of 2, density squared, or logs are another way that we end up with curved lines, or we actually fix curved lines. So I'm pointing that out because we can't, again, it goes back to the same issue that things respond differently depending on how big they are. So at a certain size of tree, we get a certain level of density versus other sizes of trees. The stocking diagrams have had utility and management, and we can think of a thinning regime that starts here with a fairly high number of trees per acre and a fairly high basal area, and presumably you can see these lines at the top are QMD lines. So here's QMD 7, then 8, 9, and so forth. So these trees are small. And this red line might represent a thinning. We take the number of trees down. We're thinning from below, so we're increasing the QMD from something like 7.5 to maybe 9 or 8.5. It grows back up. This line's just going straight up here. We're not losing trees. This is sort of an idealized situation, of course, because we're not approaching this overstock condition, so all the trees have enough growing space. So we go straight up, we're increasing basal area, we're cutting across these QMD lines, and we're heading back towards a overstock condition, and we thin again reducing number of trees per acre, increasing the QMD, and we grow again, and we might have a final harvest at some point like this. So this is a map to show the region where we want to thin. And presumably, as long as we thin in this region, we're in that range of productivity that we talked about where we're maximizing stand level productivity. There's a number of assumptions here that we'll talk about, but this is the main idea is we want to stay in that range where we're at that sort of maximum level of productivity. We don't want to go down to the point where we think we're actually going to lose productivity. Okay, let's switch to the next one. Now we're going to look at the Reineke stand density index. And this really it's an interesting approach. It's sort of a mystery in forest mensuration why this works. But basically there's this simple relationship between average diameter, QMD, actually quadratic mean diameter, and number of trees per acre. The trick is, though, they both have to be on this log scale. And so this is a log 10 scale. And what logs do is that the bigger the number you have, the smaller the increment is as you go from one size to the next. And that's probably completely unclear, but basically what it means is the difference between a 1-inch tree and a say a 5-inch tree is the same on our regular scale as between an 11-inch tree and a 15-inch tree. On a log scale, the difference between a 1-inch tree and a 5-inch tree is larger than the difference between an 11-inch tree and a 15-inch tree. And you can see that on these scales where you're jumping from 1 to 2 is a big jump, 2 to 3 is a smaller jump, 3 to 4 is yet a smaller jump, yada, yada. 9 to 10 is a tiny, tiny jump, and then you're almost jumping the same as between 1 to 2 to jump to 10 to 20. So it compresses your cloud of data. And this is part of the reason it works. But basically, what Reineke observed was if you look at things this way, you get a really nice upper level of density, so this nice A-line. Part of SDI is the sort of at the index level, which is a 10-inch tree. So SDI of 600 basically means that if you had if you have 600 10-inch trees, you reach this level, SDI level of 600. Now, as you have, say, 15-inch trees, you're going to have fewer trees, but you're still going to be on sort of that same index. So it basically pins down the lines to that 10-inch tree in a similar way to we pin down site index curves to a base to age of 50. So that's basically how these SDI lines work. And Westside Douglas fir, there's max SDI, and basically this is something like the A-line. This is that very top level of stocking, of density, that we ever view. And it's about 600 in Douglas fir on the west side. We have a lot of data from Friss, so that's going to be the next slide, excuse me. Another aspect of SDI is since we're drawing the maximum density line, we also think of this as being the self-thinning line. And what I mean by that is you start with, say, some high level of trees per acre. This is 2,000 per hectare, and some level of DBH. You'll basically grow along in DBH without much mortality because we're not at that level of density that causes mortality. And eventually the curve turns and sort of follows this self-thinning line. So in order to, as the stand grows larger, the average tree size increases, the number of trees per acre decrease in sort of an orderly way. And these lines show some long-term measurements as individual plots are heading towards the self-thinning line and then moving down it. So this SDI line is also used as the self-thinning line. In this case, you're seeing none of these, very few of them are actually reaching this line, and so there's some lack of precision here on where that line actually is, but it is intriguing to see stands moving along the self-thinning line. Okay, now we're going to look at, okay, I'm going to jump over here since I introduced it already. Okay, now this is data from Friss, and I'm plotting it in the same log space that Reineke used, trees per acre and QMD, and here's our SDI of 600. And what we're trying to capture here is that upper limit of density. And it does a pretty good job. That red line follows along pretty close to what we're seeing in Friss. The blue points are west side stands, and the green points are east side stands. But I thought this was neat, and it almost always works out this way. There's something about this mystery of SDI that it really empirically is reinforced over and over again. And I did skip one slide, so I'm going to jump back to this one. SDI has been used as a basis for stand density management diagrams, and this is pretty similar to what we saw with the Gingrich stocking diagram. So we have our line. This is our maximum density line. This is lodgepole pine. I like this one because of the annotations on it. They did some neat work in terms of drawing some additional lines. So here's our maximum density line. This gray area is the area where we're going to maximize current annual increment. So that's that flat spot on the Langsaeter curve, and as long, presumably, as we keep our density within this gray area, we're going to be in that flat area where we're maximizing productivity. They also drew in the line of crown closure that also runs parallel to the line of maximum density. So this is really our, well, it's a little different here. It's sort of like our B-line is the area, this gray area, where we want to maintain between this upper level of density and this level in order to maximize productivity. So it's another neat tool that has been developed based on these density concepts. Okay, we did that one. Okay, let's jump to Curtis's relative density. Curtis did some really interesting work on density measures in general. And when I went to visit with him, I asked him, have your thoughts changed on this topic over the years? And he pointed out that his original work was done in 1970 and 1971, and that was 40 years ago. And Bob Curtis has always been very impressive to me. He's over 80. He must be in his mid-80s now. Extremely sharp person, and in no time we were rolling on talking about maximum density. So Curtis's relative density. I'm not going to go into too much of the math that he presented, but we can think of it as a measurement of basal area compared to the maximum level basal area. So it's almost as if we're taking Reineke's line and doing something, maybe something like Gingrich did, where he had percent stocking levels reaching that 100%. And what we're seeing here is that what he's embodying, I guess I would say, is that for a particular level of basal area, or a particular QMD, excuse me, that maximum level of basal area changes. And we saw that with our data from DNR, and we'll look at that again here in a minute. So the maximum basal area varies with QMD. When you reach an RD of 100, that is presumably that maximum density line, something akin to Reineke's max SDI line. There's two ways of calculating Curtis's RD. One is just observed basal area for a stand divided by the quadratic mean diameter raised to the 1/2 power. That's the same as the square root of the quadratic mean diameter. But there's another method here that Bob has worked on recently and wanted me to point out. It's called the summation method, where you take your tree list. If you have your tree DBH and trees per acre, so the trees per acre represented by each observation in the tree list, you can raise DBH to the power of 1.5, multiply by the trees per acre, and sum these up, and then multiply by our old standard 005454, which is what we use to go from DBH to basal area. Bob prefers this method, and we'll talk about why here in a minute. So I wanted to just expose you to some of this, that Curtis's RD and SDI are a lot alike. And if you do some mathematical calculations here, since basal area is a function of QMD, we can come down and say the RD is a function of trees per acre times some sort of constant. This is that 0.005454 times QMD to the 1.5 power. Again, these are the steps to get there. SDI is trees per acre times QMD times some sort of factor, in this case divided by some sort of factor, to the 1.6 power. And so what I really want to point out is these are a little bit different. Basically, they're scaling QMD differently, in this case dividing by 10, and the powers are a little bit different. Curtis felt 1.5 was a better power than 1.6, but really they're very similar. Curtis's scales to about 100, for Douglas fir on the west side, SDI scales to about 600, but the formulations are really very similar. So how well does RD match DNR stands? When we take our first look, it doesn't look as good as Reineke's SDI, but Reineke gets the benefit of being in log-log space. That makes things look much cleaner than they are in this regular space, the kind of space we're used to dealing with. So if we look at QMD and we look at basal area, this is that 100 line. This is that line that we think is maximum density. we see a lot of stands that, based on this, would exceed an RD of 100, and I think many of us have seen those types of stands in the past. But it's not too bad. It does sort of a better job than just some straight level basal area of capturing what's going on this low end. And as we go up here, we're not quite capturing that high end as well. But this is basically what we'd expect to see as the kind of top level of RD. We also have to point out that Curtis was working in an era where with much, much less computational power than we have now, and less data. So we can be more empirical now than we used to be able to, and ask questions more specifically and really back those up with data. Our jobs as biometricians are much, much easier than they were back when Curtis was working on this. Okay, so we looked at how RD is measured. What are some of the silvicultural benchmarks? I was in touch with Bob today and asked him, what point would you call a crown closure? And he replied that he was not aware of any empirical work, but he thought RD 20 was about the point of crown closure, so perhaps that Bline. And I used the CCF method, so at what point would we reach 100% crown competition factor, and I got an RD of about 25, so we agree pretty closely. So there's been various prescriptions for thinning at different RDs, and I didn't have a lot of time to go through all of them. But I just looked a bit, and I found some that said some guidelines of how you use RD for thinning. And Curtis and some original work suggest 50 would be the point where you would thin in young scans. Some guidelines for the BLM suggest thinning when RD is greater than 60. And again, really, remember what we're trying to do is put single numbers on these values. So we're not saying thin when you reach a RD of 50 if your quadratic mean diameter is between 5 and 15 inches or something like that. We're trying to come up with numbers that sort of work across the range of mean tree size. And then what do we thin to? So what's sort of that zone in which we want to thin? And there's been various guidelines, but somewhere around 35 or 40 seems to be the point we want to thin to. And I didn't really dig deep enough to figure out what the basis was for all of these decisions. Okay, I'm going to jump into some of these different methods. I talked about the summation method versus the average method. So the average method is basal area divided by QMD to the 0.5 power. The summation method takes each individual tree and adds them together. Bob is recommending the summation method now because there are some issues with the average method. And these issues are most prevalent where we have small trees. And what happens is, there's a case here, this is from one of his publications, where we have a diameter distribution that has some big trees here and then a cohort of small trees. And the question is, should we count those or not? They tend to bring your QMD down without adding a lot of the basal area. And so as your QMD decreases, your RD basically increases at a faster level than I think Bob wants it to happen. And it seems reasonable. And if we look here, what I've highlighted here at the bottom, we have the mean method. We just did the basal area and QMD. We get an RD of 95.4. We use the summation method. We get an RD of 68.5. If we only look at the large trees, no big deal. But if we are looking at large and small trees, the QMD method is going to have a much larger impact to small trees. And it seems to be more stable if we use the summation method. If you're collecting data in the field, the summation method is just as easy to implement as the QMD method. So from that perspective, I would just use the summation method. Okay. As Ralph and I were talking, one of the topics was how do we measure RD in the field? And I think what he was talking about in particular was difficult situations. I think in a typical stand, it's not hard to do. We put in a grid of plots and we measure those plots. We go back and we do our calculations. But what about other situations? And really this discussion relates to all inventory, all measurements. It's not just related to RD, but I wanted to bring this up because there's cases where we have particular targets, say in a riparian area, and we want to understand how to measure RD effectively. The first question is, what's the population of interest? And we typically define that with some sort of polygon. And this is one of our first polygons here. And if this is our population of interest, if you capture it this way and we want to try to represent this polygon, we can't just sample where there's trees. We have to sample everywhere. And I'll expand upon this here. So what's the population of interest? We typically is defined by some sort of area of interest polygon. I have people ask me, is it okay to leave out roads, landings, etc.? Should we just skip those things if we find them? And yes, if it's not part of your population, then don't measure it. But you have to be sort of transparent about this. You can't decide in the office, this is my population of interest, this 50-acre polygon, and then in the field decide, actually my population of interest are just these leaf tree patches that are only maybe 5 acres. So you have to ahead of time decide where your population of interest lies, and if you cut out roads and if you cut out other features, fine, as long as that's what your population of interest is. And one way of sort of checking about this is, do the acres you measure equal the acres you're reporting? And what I mean by that is, if you're in the field and deciding not to measure certain features, you're leaving out acres. And it's okay as long as you've actually sort of ahead of time said, I'm leaving those acres out. So the area of that polygon and how many acres you're reporting, this is a 50-acre stand or whatnot, it should measure the area it should equal the area you've actually measured. So going back, thinking of plot locations, every point within the area of interest should have an equal chance of measurement. We can do that using a square grid or hexagonal grid. We have tools to do this in ArcGIS. And then measuring RD, we can use fixed radius plots where we record the diameter of each in tree. We can even estimate the diameter of those trees, say to every 2 inches. And then we get the expansion factor, the trees per acre from plot size. With variable radius plots, we also would want to record the diameter of each in tree or estimate it. And then we get trees per acre from both the diameter and the BAF factor. I don't recommend mixing plots, and I've seen when I was in Pennsylvania, they did something very similar to that with the Gingrich stocking diagram where they measured basal area using variable radius plots and trees per acre using fixed radius plots. And I recommend not doing that because you're sampling with 2 different levels of intensity, and you can get nonsensical answers. So you can get your trees per acre answer being pretty different from your basal area answer. So I would recommend that not doing that. I would be much happier using a variable radius system and making an estimate of diameter to reduce time if that's a factor than mixing plot types. So how about edges? This is a question I'm asked a lot. And there's 2 issues that revolve around edges. One is, are edge trees different from the interior? If I skip edges, am I going to get a sample that's not representative of the whole population of interest? And then the other issue is, do you have plots that have area that extends outside the area of interest? And there's a couple strategies of dealing with edges. One is to avoid edges. This is, again, not recommended. But you're probably okay if condition 1 is met. So in other words, those edge trees are the same as your interior trees. If you had a recent harvest where that edge is sort of arbitrarily drawn, you're probably okay. If you've had an edge that's been there for a number of years, those edge trees are going to develop differently than your interior trees, and you're probably not okay. The other strategy is doing some sort of edge correction, and there's a couple of them out there. And I'm going to talk about the mirage method. So imagine we have our area of interest, we lay a grid of points on it. Some of those points fall near an edge. When we go out and measure that plot, that part of that plot seems like it's outside of the polygon we're interested in. And if we don't do anything, we're going to undercount trees because we're basically measuring part of the part of the area outside the polygon. And so the mirage method is pretty easy to implement. If you think part of your plot is outside the area of interest, you measure a second plot that's equal distance from the edge as your first plot. So you would measure from your first plot to the edge and then follow along that same line in equal distance and then establish a second plot. And this works with both fixed radius and variable radius plots. It's more difficult to know when you're outside with a fixed radius plot because it depends on how big the tree is and your BAF factor to know how far away you might pick up a tree. But if you're close, you can just do a mirage method. And this is an example here. There's our plot center. This is a fixed radius, and we're partly outside of the unit. We collect this plot, then we establish a second plot. We don't count any of these if there happens to be trees out here. We don't count any of them until we're back into our first area, and then we count those trees. And these become part of this first plot. They're basically double counted, and that deals with our edge issues in an appropriate way. Okay, real quickly, Ralph, do I need to stay on schedule here? Or? 5 minutes. Okay. We'll talk about what to do with the data once we get back. Say we have 3 plots. I would never measure 3 plots. I would at least measure 5. But let's say we have 3 to make it simple. And we have a BAF factor. So here's those DBHs we measured, and we just measured them in 2-inch classes. And maybe we estimated those values. We can use the standard formula to go from a diameter measurement and a BAF factor to trees per acre. And then we use the summation formula, and I already brought in the fact that we have 3 plots into that formula as well. And then we can just sum those up and get an RD value. So this is the summation method, and this is a more stable method when you're dealing with small trees in particular. If you're dealing in stands that are fairly uniform, you can do it either way and get the same answer. Okay, I just want to touch on just a couple additional topics on density that are outside of this sort of focused on RD, and I'll jump through these kind of quickly. One question I've had is, does RD work better than basal area or other measurements for estimating canopy cover? So in some cases, we may have a goal of maintaining a particular canopy cover, and we don't go out there and measure canopy cover. We measure something else to determine whether we're reaching that canopy cover level based on a relationship. Okay, so here's basal area. This is from the inventory, our current inventory work, where we're measuring canopy cover and basal area and everything we need to measure to calculate both basal area and RD. And this is a statistical fit, a nonlinear fit, this red line. And what it comes down to is from what we see in our work, basal area is just as good of a predictor of canopy cover as RD. And it's actually a little better statistically. And what you see here is there's not many points out in this area for basal area, and for RD, there's a little bit more scatter. So it actually works a little bit better than RD for relating canopy cover to basal area. Incidentally, I said before I came up with numbers. I came up with a number of about 25 for that point of reaching complete canopy closure or cover, excuse me, or a trunk competition factor of 100. Bob Curtis said about 20, and we're pretty close. We're pretty close. Both of our measures are around here on relative density in terms of where we would expect to have 100% canopy cover. But bottom line is basal area works just as well based on our numbers. And how about canopy closure? It's the same story. Basal area works as well as RD in terms of estimating canopy closure, and I'm not going to go into the difference between those two right now. How about that Langsaeter curve? Is there an area of density where productivity is about equal? This is a graph from a long-term study called the LOGS study. This is another study that Bob Curtis was very active in. It's called its level of growing stock. And this study was basically, there was a repeated thinnings to maintain a certain level of growing stock, a certain density per se, over time. And one of the interesting things I've found out of the study is that the control line, the unthinned line, has always had higher productivity than any of the thinning regimes. And this one includes both standing volume and past thinning, so the cumulative productivity. So the unthinned line stand has always had the highest productivity. So basically, in terms of that, the Langsaeter curve, it keeps going up. As far as we've seen, as density increases, our cumulative productivity in terms of wood growth also increases. Talking with Bob about this, he said, well, you know, that's true, but really most of our treatments have had pretty similar levels of productivity. So in a general sense, yes, there's this range where more or less you're getting the same level of productivity over time. So that was pretty interesting. I think the bottom line here is you're probably going to get the most productivity by not thinning, but that's only one of the issues that goes, or one of the factors that goes in the decision whether or not to thin. I mentioned earlier that we want measures that don't differ among site classes and other factors. This would be, it's very convenient when you can sort of throw one number out and it works everywhere. But there's been additional work with more sophisticated statistical methods that were available before to try to tease these things out. And something that's been known a long time is shade-tolerant species are going to have a higher maximum density level than less tolerant species. Something that was found in this particular work that I was involved in was that natural stands have a higher level of density than planted stands. This difference is pretty substantial. And productive sites have a higher level of maximum density than less productive sites, and that difference is fairly small. I think in natural stands, trees, you know, in places where you have abundant natural regeneration, trees are very good at finding every nook and cranny in which there's enough resources to grow. When we go and plant trees, we are telling trees where to grow. In natural stands, they're figuring out where to grow, and they're better at it than we are, is what I take from this. Final point is, does all the action happen above ground? Everything we've talked about our thinning regimes and maximum density and so forth, we're talking about measurements done above ground as if everything happens there. And it's very convenient, once again, to base things on what's happening above ground because we can measure it. We can't measure what's going on underground. But there's also stuff going on underground. I just want to make that point. This is a study that was done by Warren Devine, who also works for the DNR now and was one of my colleagues at the P&W Research Station, where they were looking at understory trees, and they trenched blocks of understory trees to reduce root competition, and they saw a significant increase in growth. So the main point here is don't forget to look underground as well. It's above ground when you're thinking about density and utilization of resources. And that's all I have.
Thank you, Peter, for helping us out this afternoon with a very thorough discussion of forest density measures. If you have questions, we have a little bit of time. If you want to go ahead and post that in your question pane, I'll ask Peter to pose an answer. I'm going to stop the recording right now. So